Imagine standing at the edge of an abyss so profound that not even light can escape its grasp. You take one step forward. In that instant, you cross a threshold from which nothing, not matter, not energy, not even information itself, can ever return. Or so we thought. In April 2019, humanity captured the first direct image of a black hole's event horizon, a glowing ring of light surrounding absolute darkness. 6.5 billion times the mass of our Sun, sitting at the heart of galaxy M87. The image was remarkable, but it revealed something far more troubling than anyone expected. Every observation we make of black holes confirms a disturbing possibility. These cosmic monsters appear to violate the most fundamental law of quantum mechanics. They destroy information, completely, irreversibly, forever. If this is true, then quantum mechanics, the theory that describes literally everything in our universe, is fundamentally broken. The greatest minds in physics have spent 50 years wrestling with this paradox. Stephen Hawking changed his position 3 times. Einstein refused to believe it. And today, the evidence suggests reality itself might be a hologram projected from the edge of space-time. What if the universe doesn't work the way we think it does? What if everything we know about reality is emerging from somewhere else entirely? Today, we journey through evidence that challenges everything we understand about existence itself. Prepare yourselves. We begin. In 1915, Karl Schwarzschild, a German physicist serving on the Russian front during World War I, did something extraordinary. While calculating artillery trajectories by day, he spent his nights solving Albert Einstein's recently published field equations of general relativity. Within months, Schwarzschild discovered something that would haunt physics for the next century. His calculations revealed that if you compressed enough mass into a small enough space, you would create a region of space-time so warped that it would seal itself off from the rest of the universe, a mathematical point of no return. He called it the Schwarzschild radius, but we know it by another name, the event horizon. Einstein himself didn't believe such objects could exist in nature. He thought the mathematics must be breaking down, revealing some flaw in his own theory. For decades, most physicists agreed. Black holes were mathematical curiosities, nothing more. Then came 1964. That year, a rocket-borne detector discovered an intense source of X-rays in the constellation Cygnus. Scientists named it Cygnus X1. The radiation was behaving strangely, flickering rapidly, suggesting the source was compact, very compact. By 1971, observations revealed something shocking. Cygnus X1 was orbiting a blue supergiant star, pulling matter from it at an astonishing rate. The infalling material accelerated to nearly the speed of light, heating to millions of degrees and screaming in X-rays as it spiraled toward nothing. No light came from the source itself, only darkness. The calculations were inescapable. This invisible object contained at least 10 times the mass of our Sun, compressed into a region smaller than a city. A black hole, real, observable, devouring matter right in front of our telescopes. Stephen Hawking famously bet against its existence. He lost that bet, but in losing it, he stumbled upon something far stranger. Here's what we thought we knew about black holes. Once something crosses the event horizon, it's gone. Not just gone from our view, gone from the universe entirely. All information about that object, its composition, its quantum state, its history disappears forever into the singularity at the black hole's center. To most physicists in the 1960s, this seemed reasonable, disturbing perhaps, but consistent with general relativity. But there was a problem, a fundamental problem that would eventually fracture our understanding of reality itself. Quantum mechanics has one absolute law: information cannot be destroyed, ever. Think of it this way: if you burn a book, the information isn't truly destroyed. In principle, if you could track every atom of smoke, every photon of light, every particle released in the fire, you could reconstruct the exact text of that book. The information is scrambled, spread throughout the universe, but it still exists. This principle, the conservation of quantum information, is as fundamental to physics as the conservation of energy. Black holes appeared to violate this principle completely. In 1974, Stephen Hawking published a paper that would change everything. He had been studying what happens at the quantum level right at the event horizon of a black hole. His calculations revealed something nobody expected. Black holes aren't eternal. They radiate, slowly, almost imperceptibly, but inevitably. Quantum fluctuations at the event horizon create pairs of particles. One falls in, one escapes. To an outside observer, the black hole appears to emit radiation. We call it Hawking radiation. This means black holes eventually evaporate completely. Given enough time, an incomprehensibly long time, but finite, every black hole will irradiate its entire mass and vanish. Here's where the crisis emerges. Hawking's calculations showed that this radiation is completely random, thermal, containing no information about what fell into the black hole. So when a black hole evaporates, what happens to all the information that fell in? All the quantum states of every particle, every atom, every star that crossed the event horizon. It's gone, erased from the universe forever. Hawking had proven that black holes destroy information. But quantum mechanics says information cannot be destroyed. Both cannot be true. This is the information paradox, and the evidence forces us to confront an uncomfortable possibility. Either quantum mechanics is wrong, general relativity is wrong, or something far stranger is happening at the edge of black holes. Fast forward to April 10, 2019. The Event Horizon Telescope collaboration released an image that made headlines around the world. For the first time in history, we were looking directly at a black hole's shadow. The black hole at the center of galaxy M87, 55 million light-years away, appeared as a dark circle surrounded by a bright ring of incandescent gas. The darkness at the center measured approximately 40 billion kilometers across, larger than our entire solar system. But here's what the image really showed us. The event horizon is real. It's not a mathematical abstraction. It's an actual boundary in space-time where the rules change fundamentally. Scientists measured something crucial. The temperature of the radiation near the event horizon reached billions of degrees. But when they calculated the temperature of Hawking radiation for a black hole this massive, they found something disturbing. It should be 0.00000000000017 degrees above absolute zero. This massive discrepancy tells us something profound. We can observe what goes into black holes with perfect clarity, but whatever comes out provides virtually no information about what went in. On September 14, 2015, the LIGO observatory detected ripples in space-time itself. Two black holes, each about 30 times the mass of the Sun, had spiraled together and merged. The collision released more energy than all the stars in the observable universe combined for a fraction of a second. Since then, we've detected over 90 such events. Each one provides detailed information about the black holes before they merge, their masses, their spins, their orbital characteristics, precise measurements down to decimal points. But here's what troubles physicists. After the merger, we get clean, simple gravitational wave signatures that tell us about the final black hole's mass and spin. Nothing more. All the complex information about the original black holes, their formation histories, what they consumed, their detailed quantum states, appears to vanish into the merger. Two unique objects become one simple object, and the difference is radiated away as gravitational waves. Except gravitational waves, like Hawking radiation, appear to be generic. Mathematical analysis of LIGO data shows the signals match the predictions of general relativity perfectly, but they're too simple. They don't encode enough information to account for the detailed quantum states of the original black holes. The information appears to be destroyed with each merger we observe. In 1995, physicist Leonard Susskind was studying the mathematics of string theory when he discovered something extraordinary. He found that all the information about everything inside a volume of space could be encoded on the boundary of that space. Think of it like this. Imagine all the information in a room. Every particle, every field, every quantum state could be perfectly described by a two-dimensional pattern on the walls. The 3D interior is somehow redundant, a projection. This holographic principle was bizarre enough, but when Susskind applied it to black holes, something clicked into place. The surface area of a black hole's event horizon, measured in Planck units, the smallest meaningful units of space, exactly matches the maximum amount of information that black hole could possibly contain. Not its volume, its surface area. It's as if everything that falls into a black hole gets encoded onto its event horizon like a hologram. The 3D object creates a 2D record. Observations support this in an eerie way. Jacob Bekenstein had calculated in 1972 that black holes have entropy, a measure of information content. But he found that this entropy is proportional to the event horizon's area, not its volume. Every subsequent observation has confirmed this relationship. Supermassive black holes, stellar mass black holes, the mergers detected by LIGO, all follow the same pattern. Information appears to be stored on the surface, but this represents just one piece of a much larger puzzle hidden in the mathematics of quantum gravity. Part B. Deeper implications. The firewall paradox. In 2012, 4 physicists, Ahmed Almiri, Donald Morolf, Joseph Polchinski, and James Sully, discovered something that sent shockwaves into the physics community. They were studying what happens to Hawking radiation as a black hole ages. Their calculations revealed an impossible situation. If information is preserved during black hole evaporation, then the event horizon cannot be the calm boundary general relativity predicts. Instead, they found that the event horizon must be a firewall, a surface of incredibly high-energy particles that would instantly incinerate anything that tried to cross it. This contradicts Einstein's principle of equivalence, which says that freely falling across an event horizon should feel like floating in empty space. Nothing special should happen at that boundary. Think about what this means. We've observed stars orbiting supermassive black holes, watched matter spiral across event horizons. Everything we see is consistent with a smooth crossing, no firewall. But if there's no firewall, then information really is destroyed, and quantum mechanics is violated. The most remarkable discovery involves the mathematical proof itself. The AMPS team showed that you cannot have a smooth event horizon, general relativity, Hawking radiation, quantum field theory, information preservation, quantum mechanics, no faster-than-light signaling, special relativity. At least one of these fundamental principles must be wrong. In 2013, Juan Maldacena and Leonard Susskind proposed something radical. They suggested that quantum entanglement, the mysterious connection between particles that Einstein called spooky action at a distance, might literally be the same thing as wormholes connecting different regions of space-time. Their paper titled ER equals EPR suggested that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, quantum entangled particles. Here's why this matters for black holes. When particles become entangled near the event horizon of a black hole, they might be creating microscopic wormholes connecting the interior to the exterior. Recent mathematical studies have found that the amount of entanglement between the inside and outside of a black hole exactly matches what you'd need to maintain information transfer through quantum connections. Observations of black hole binary systems show something curious. The gravitational waves they emit contain subtle correlations, patterns that appear at scales too small to be explained by classical physics alone. Some theorists interpret these as signatures of quantum entanglement operating at cosmic scales. If ER equals EPR is correct, then information never falls into a black hole at all. It remains connected to the outside universe through a vast web of quantum entanglement. The black hole's interior and exterior are the same thing, viewed from different perspectives. In 2016, Stephen Hawking, along with Malcolm Perry and Andrew Strominger, published a paper about soft hair on black holes. For decades, physicists believed black holes could only be described by three numbers: mass, charge, and spin. This is called the no-hair theorem. Black holes are smooth and featureless, with no complexity beyond these basics. But Hawking's final work revealed something different. Black holes can have soft hair, subtle quantum features at the event horizon that carry information. These aren't observable in the traditional sense, but they're mathematically necessary to preserve quantum information. The paper showed that these soft modes, low-energy quantum fluctuations, could encode unlimited amounts of information on the event horizon without violating any known physics. Recent calculations suggest these soft modes create patterns in the gravitational field around black holes. Patterns too subtle to detect with current technology, but theoretically observable with next-generation gravitational wave detectors. The accumulating evidence points toward a radical conclusion. Our three-dimensional reality might be a hologram projected from a two-dimensional surface. This isn't science fiction. The mathematical framework called the ADS-CFT correspondence was proven in 1997 by Juan Maldacena. It shows that a quantum field theory in n dimensions can be perfectly equivalent to a gravitational theory in n+1 dimensions. Think of it like this. Imagine you're watching a 3D movie. The rich, detailed, three-dimensional world you see is actually generated from patterns of light on a flat screen. In a very real mathematical sense, the 2D screen and the 3D image contain exactly the same information. String theorists have shown that our universe might work the same way. Everything we experience, matter, energy, space-time itself, might be an emergent hologram projected from information encoded on a distant two-dimensional surface. This forces us to reconsider fundamental assumptions about the nature of reality. You're not inside a universe, you're part of a holographic projection generated by quantum information on a boundary. Black holes are where this becomes obvious. At the event horizon, the holographic nature of space-time breaks down into something we can actually study. The three-dimensional interior becomes explicitly equivalent to two-dimensional information on the surface. Every calculation in string theory, every simulation of quantum gravity points to the same conclusion. Information is never destroyed because it was never really inside to begin with. In 2019, physicists made a breakthrough that might finally resolve the paradox. Jeff Pennington, working with Ahmed Almhiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, developed what's called the island formula. This mathematical framework describes how information escapes from black holes. The key insight involves something called page time, named after physicist Don Page. It's the moment when an evaporating black hole has radiated away about half its original mass. Page calculated in 1993 that this should be when information starts coming out faster than it goes in. The island formula explains exactly how this happens. It shows that islands of spacetime inside the black hole remain quantum mechanically connected to the Hawking radiation outside. These islands grow over time until, at page time, they encompass most of the black hole's interior. What scientists at the Institute for Advanced Study, Princeton, Caltech, and Stanford discovered is remarkable. When you properly account for quantum entanglement between the black hole interior and the radiation, the information paradox disappears. Mathematically, it was never there. The information comes out, but it's scrambled in the most complicated way possible. To decode it, you'd need to capture and analyze every single particle of Hawking radiation for the entire evaporation process, which for a solar mass black hole would take 10 to the 67 years. Leading physicists like Leonard Susskind now believe this is the solution. Information is preserved, but it's hidden in correlations so subtle and complex that for all practical purposes it looks destroyed. The catch: this solution requires that space-time at quantum scales works completely differently than we imagine. We're now entering an era where these theoretical predictions might become testable. The upcoming Laser Interferometer Space Antenna, LISA, scheduled to launch in 2035, will detect gravitational waves at frequencies impossible to observe from Earth. LISA will be sensitive enough to potentially detect the subtle quantum correlations in gravitational waves from black hole mergers, the signatures of information being preserved in ways general relativity alone cannot predict. The next generation Event Horizon Telescope is already in development. With 10 times the resolution of the 2019 image, it might reveal subtle asymmetries in black hole shadows, irregularities that could represent the quantum soft hair Hawking predicted. Even more ambitious, researchers at the Perimeter Institute and the Max Planck Institute are developing theories about how to detect holographic effects in cosmic microwave background radiation. If space-time is fundamentally holographic, there should be subtle correlations in the oldest light in the universe, patterns that don't make sense in conventional physics, but would be signatures of information encoded on a cosmic boundary. Recent breakthroughs in quantum computing have enabled simulations of quantum gravity effects that were impossible just 5 years ago. In 2022, Google's quantum AI team simulated a tiny quantum system that behaves like a holographic black hole. They observed information scrambling and recovery exactly as predicted by the island formula. It was a toy model, not a real black hole, but it proved the mathematics works. The implications stretch far beyond black holes. If information is fundamentally preserved at black hole event horizons, then it's preserved everywhere in the universe. This means the second law of thermodynamics, the tendency toward disorder, is not fundamental, but emergent. At the deepest level, all processes are reversible. The holographic principle suggests that space itself is emergent, not fundamental. What we perceive as distance and dimension might be convenient macroscopic descriptions of something else entirely, quantum entanglement networks at the Planck scale. Physicists like Mark van Ramsden at the University of British Columbia have shown that space might literally be quantum entanglement. Entanglement builds space-time, he says. The geometry of the universe emerges from patterns of quantum information. This has profound implications for cosmology. The Big Bang might not have been the beginning of space-time, but a phase transition in a deeper quantum information structure. The expansion of the universe might be the growth of entanglement networks. Some researchers are exploring even more radical possibilities. Consciousness itself might be related to information integration at quantum scales. If reality is fundamentally about information processing, then complex information integrating systems like brains might be tapping into something universal. Perhaps most exciting, black holes are now our laboratories for testing quantum gravity. The LISA Virgo-Cagra collaboration detects black hole mergers weekly. Each event provides data about how quantum information behaves in the strongest gravitational fields in the universe. Astronomers have discovered dozens of supermassive black holes in the early universe that shouldn't exist. They formed too quickly, grew too massive. Some theorists suggest this might be evidence that black holes preserve information more efficiently than we thought, allowing them to grow faster by reusing quantum information. The black hole at the center of our galaxy, Sagittarius A star, is being monitored constantly. In 2022, the Event Horizon Telescope captured its image. In the coming years, next-generation instruments will watch matter fall across its event horizon in real time. Frame by frame, we'll observe information crossing the point of no return. What we learn there will tell us whether quantum mechanics, general relativity, or our entire conception of reality needs to be rewritten. The most profound implications emerge when we consider what all this evidence means for the universe as a whole. Here's what the evidence forces us to consider. If black holes encode information holographically on their event horizons, then perhaps the entire universe does the same. Our observable universe has a boundary, a cosmic horizon beyond which light hasn't had time to reach us since the Big Bang. This horizon has a finite surface area, roughly 10 to the 123rd Planck areas. According to the holographic principle, this area determines the maximum information content of our observable universe, about 10 to the 123rd bits. That's the total number of yes or no questions you can ask about everything that exists within our cosmic horizon. This number is incomprehensibly large, yet it's finite. What this means, our universe has a finite resolution. There's a maximum level of detail. At some scale, reality becomes discrete, pixelated in a sense. Everything you've ever experienced, every thought you've had, every particle in every atom in every star, all of it could be encoded on a two-dimensional surface surrounding our observable universe. You might not be inside the universe at all. You might be the universe, viewed from within a holographic projection. If information truly is never destroyed, then everything that has ever happened in the universe still exists somewhere. Every moment of your life, every choice you've made, every possibility that didn't occur, all of it remains encoded in the quantum state of the universe. Nothing is ever truly lost. This has implications for time itself. Physics equations work just as well backward as forward. The arrow of time, our sense that the future is different from the past, might be an illusion created by our perspective within the hologram. Some physicists, like Carlo Rovelli, suggest time itself is emergent. What we call time is really the evolution of quantum entanglement patterns. The past is just one configuration of information. The future is another. Both exist equally in the timeless quantum mathematics. If this is true, then the universe is like a vast cosmic hard drive, storing every moment in an eternal now. The flow of time we experience is us reading one bit of information after another. The holographic principle and the information paradox lead to an unsettling possibility that serious physicists are now discussing openly. If reality emerges from quantum information at a boundary, if space-time itself is an emergent hologram, if the universe has finite information content encoded in a discrete structure, then in what meaningful way is our universe different from a computer simulation? This isn't wild speculation, it's the logical conclusion of accepted physics. Physicist James Gates discovered in the equations of supersymmetry something extraordinary: error-correcting codes identical to those used in computer browsers and data transmission. Deep in the mathematics describing fundamental particles, there are literal codes for detecting and correcting errors. Why would the universe need error-correcting codes unless it was, in some sense, processing information? Quantum computers are now simulating quantum field theories, creating mini-universes that follow the same rules as ours. As these simulations become more sophisticated, the entities within them would have no way to know they're simulated. They'd observe quantum mechanics, relativity, information preservation, all emergent from their computational substrate. Are we any different? The evidence doesn't prove we're in a simulation, but it does prove that the question is now a legitimate scientific inquiry, not philosophy. Despite all the progress, fundamental mysteries remain. We still don't have a complete theory of quantum gravity. String theory, loop quantum gravity, asymptotic safety, each approach has insights, but none fully explains what happens at the Planck scale where quantum mechanics and general relativity collide. The firewall paradox hasn't been definitively resolved. We have mathematical solutions like the island formula, but we don't know if nature actually implements these solutions or something else entirely. We've never detected Hawking radiation. The temperature is too low, the signal too weak. It remains a theoretical prediction, beautifully supported by mathematics, but lacking direct empirical confirmation. And perhaps most troubling, If information is preserved through such complex scrambling that it takes longer than the age of the universe to decode, is it really preserved in any meaningful sense? The great physicist John Wheeler said, "It from bit, everything that exists, every particle, every field, every force, emerges from binary information, from bits." The information paradox has led us to this conclusion. Reality is made of information, structured by quantum mechanics, projected as a hologram, and somehow encoded on boundaries we cannot see. We're not observers of reality, we're part of the information itself. We began at the edge of a black hole's event horizon, confronting a paradox that threatened to break physics itself. We've journeyed through 50 years of discoveries. Hawking radiation showing that black holes evaporate. Gravitational waves revealing mergers that seem to destroy information. The holographic principle suggesting reality is a projection. Quantum entanglement possibly connecting everything through microscopic wormholes, and mathematical breakthroughs like the island formula offering solutions at the edge of comprehension. We've learned that the question, what happens when you fall into a black hole, cannot be answered without reconsidering the nature of reality itself. The current scientific consensus is remarkable. Information is almost certainly preserved. The universe is fundamentally holographic. Space-time emerges from quantum entanglement. Everything connects to everything through patterns of information we're only beginning to understand. But here's what makes this journey extraordinary. We don't have the final answer yet. The information paradox has transformed from a threat to physics into a doorway revealing vistas we never imagined. Black holes aren't just cosmic monsters, they're laboratories where the universe reveals its deepest secrets, windows into the quantum structure of space-time itself. The next decade will bring observations that might finally close the case, or open entirely new mysteries. LISA will detect gravitational waves at frequencies that could reveal quantum gravity effects. Next-generation telescopes will image event horizons in unprecedented detail. Quantum computers will simulate bigger and better toy universes. And somewhere, someone will have an insight that connects all these pieces into a complete picture of reality. Perhaps you're reading this in a world where that breakthrough has already happened, where we finally understand what happens at the moment of crossing an event horizon, where the marriage of quantum mechanics and gravity is complete. Or perhaps the mystery deepens. Perhaps what we think we know today will seem as quaint as Einstein's rejection of black holes. Either way, this is humanity's great adventure, following the evidence wherever it leads, no matter how strange the destination. The universe is vast, its mysteries endless, and the most profound truth of all might be this: we are the universe trying to understand itself, encoded as information in a cosmic hologram, asking questions at the edge of black holes. The journey continues. But we're not done, not even close, because while the holographic principle explains where information goes, it doesn't explain what black holes actually are at the quantum level. This is where string theory enters the story. In 1996, Andrew Strominger and Kamran Vafa at Harvard made a breakthrough that sent shockwaves through theoretical physics. They calculated the exact entropy of certain theoretical black holes by counting quantum states. Think about what this means. Bekenstein had shown that black holes have entropy proportional to their surface area. But what is entropy? It's a measure of the number of different microscopic configurations that produce the same macroscopic state. For a gas in a room, Entropy counts how many ways you can arrange the molecules while keeping the same temperature and pressure. High entropy means many possible arrangements. But black holes appeared to have no internal structure, just smooth event horizons characterized by mass, charge, and spin. How could something so simple have entropy? Strominger and Vafa showed that in string theory, black holes are made of fundamental strings and higher dimensional objects called D-branes, woven together in intricate configurations. They calculated exactly how many ways these strings could be arranged to create a black hole with specific properties. The result matched Bekenstein's formula perfectly, to the exact decimal point. For the first time, physicists could see inside a black hole at the quantum level, not empty space punctured by a singularity, but a dense web of quantum strings vibrating in higher dimensions. This led Samir Mathur at Ohio State University to propose something radical in 2003. Black holes don't have event horizons at all. What we call the event horizon, Mathur suggested, is actually the outer edge of a fuzzball, a chaotic tangle of strings extending throughout the region we thought was empty space. When something falls toward a black hole, it doesn't pass through a boundary into an interior. Instead, it becomes entangled with the fuzzball, its quantum information spreading throughout the entire structure. There's no interior, no singularity, no paradox. The event horizon we observe from far away is an emergent feature, like how individual atoms in your computer screen merge into a smooth image when viewed from a distance. Get close enough and the smoothness dissolves into quantum chaos. Recent calculations support this picture in surprising ways. Physicists have found that the number of possible fuzzball configurations for a black hole exactly matches its entropy. Every microstate, every possible quantum arrangement corresponds to a slightly different fuzzball. This means every black hole is unique at the quantum level, even if they look identical from the outside. The information isn't destroyed because it never falls in. It becomes part of the surface structure. But here's the problem. If the event horizon is really a fuzzball, then anything approaching it should hit the surface and bounce off, creating observable effects. We should see evidence of this in the X-rays from accreting black holes. We don't. The event horizon appears smooth, exactly as general relativity predicts. In 1993, Leonard Susskind, Laris Thorlacius, and John Uglum proposed a solution so strange that it challenges our concept of objective reality itself. They called it black hole complementarity. The idea, both descriptions are correct depending on your reference frame. An observer falling into a black hole experiences a smooth journey across the event horizon, exactly as Einstein predicted. Nothing special happens. They pass through and continue toward the singularity, taking their quantum information with them. But an observer watching from outside sees something completely different. From their perspective, the infalling matter never quite reaches the event horizon. Time dilation slows it down, spreading it out across the surface. Eventually, it gets scrambled and re-emitted as Hawking radiation. Both perspectives are real, both are complete descriptions, but they cannot be combined into a single objective picture. This sounds like science fiction, but it's based on a rigorous principle. No single observer can verify both stories. You can't fall into a black hole and then fly back out to compare notes with someone who watched. The event horizon prevents any contradiction from being observable. Information is both destroyed and preserved, depending on who's asking. Quantum mechanics already shows us that reality depends on observation. Black hole complementarity takes this to its logical extreme. There is no single objective answer to what happens at an event horizon. reality itself splits along observer-dependent perspectives. For decades, the information paradox remained theoretical. Then came 2019, the year that everything changed. Jeff Pennington at Stanford was studying semi-classical quantum gravity, the intersection between quantum field theory and classical spacetime, when he discovered how to properly calculate the entropy of Hawking radiation. Previous calculations had missed something crucial. They hadn't accounted for the quantum entanglement between the radiation and the black hole's interior. When Pennington included these quantum corrections, he found something remarkable. The entropy of Hawking radiation didn't increase forever. Instead, it reached a maximum at page time, the moment that the black hole has evaporated halfway, and then decreased. This is called the Page curve. Page had predicted it in 1993 based on pure quantum mechanics, but no one could derive it from first principles using gravity. The fact that calculations disagreed with the Page curve was considered proof that information was destroyed. Pennington's calculation matched the Page curve exactly. Within months, Ahmed Almary, Netta Engelhardt, Donald Marloff, and Henry Maxfield published complementary papers using different approaches. They all found the same thing. When you properly account for quantum corrections to gravity, information comes out of black holes in exactly the way quantum mechanics requires. The key insight was the island formula, a mathematical expression that identifies regions inside the black hole that remain quantum mechanically accessible to the outside radiation. Here's how islands work and why they're so profound. Imagine a black hole evaporating. Traditionally, we thought the black hole interior was completely separate from the Hawking radiation outside. The event horizon was an absolute barrier. But quantum mechanics doesn't respect this separation. Through quantum entanglement, regions inside the black hole, the islands, can be in superposition with the radiation outside. Early in the evaporation process, the islands are small. Most of the black hole's interior is still causally disconnected from the outside. The entropy of the radiation increases as the black hole shrinks, just as classical calculations predicted. But as the black hole continues to evaporate, something remarkable happens. The islands grow. More and more of the interior becomes entangled with the exterior radiation. At page time, the islands suddenly encompass most of the black hole. The dominant contribution to the radiation's entropy switches from the radiation itself to the quantum entanglement with the interior. From this point forward, the radiation's entropy decreases. Information flows out faster than new Hawking radiation is produced. By the time the black hole completely evaporates, all the information has escaped, perfectly scrambled across the radiation, but preserved. Calculations published in Physical Review Letters and the Journal of High Energy Physics between 2019 and 2020 showed this works for every type of black hole: Schwarzschild, Kerr, Reissner-Nordstrom, and even ADS black holes in string theory. The information paradox was solved mathematically, definitively. But the solution reveals something even more profound about the nature of spacetime. The island formula doesn't just calculate entropy, it tells us something fundamental about how spacetime is constructed. The boundaries of islands are called quantum extremal surfaces. These are special locations in spacetime where quantum entropy is minimized. They're not fixed positions, but dynamic, evolving surfaces that track the flow of quantum information. What Netta Engelhardt at MIT discovered is extraordinary. These quantum extremal surfaces are fundamental. They're not just mathematical tools, they're the real structure underlying spacetime geometry. Think about what this means. We thought spacetime was fundamental and quantum information lived within it. But the island formula suggests the opposite. Quantum information is fundamental, and space-time geometry emerges from how that information is organized. The event horizon. String theory isn't the only game in town. An alternative approach called loop quantum gravity offers a completely different picture of what happens at black hole event horizons. Loop quantum gravity was developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin starting in the 1980s. Unlike string theory, which requires extra dimensions and exotic particles, loop quantum gravity works with the space-time and quantum mechanics we already know. The key insight? Space itself is quantized, not continuous but grainy. Imagine zooming into the fabric of space with infinite magnification. According to loop quantum gravity, you'd eventually reach a scale, the Planck scale, about 10 to the negative 35 meters, where space becomes discrete, individual atoms of space connected in a vast network. These quantum loops weave together to form space-time. Matter and energy are excitations, vibrations in this network. When you apply this to black holes, something remarkable happens. The singularity disappears. In general relativity, the singularity is a point of infinite density where physics breaks down. But in loop quantum gravity, space can't collapse to zero volume. There's a minimum possible size, enforced by quantum mechanics. What replaces the singularity? Calculations by Carlo Rovelli and Francesca Vidotto suggest that when matter collapses to the Planck density, the maximum possible density in quantum space, it bounces. Like a ball hitting a wall, except the wall is a quantum limit on how much mass can be compressed into a region of space. The collapsing matter rebounds outward. From the inside, the black hole transforms into its opposite, a white hole, an object that expels matter instead of consuming it. But here's the strange part. This bounce doesn't happen in our time frame. Due to extreme gravitational time dilation, the bounce might take billions or trillions of years as measured by outside observers, even though it happens almost instantly for the matter itself. Hawking radiation becomes reinterpreted. It's the quantum tunneling of information from the collapsing interior to the expanding white hole interior, slowly leaking out across the event horizon. Information isn't destroyed because the black hole is really a black hole-white hole pair, connected by a quantum bounce at the center. The information just takes an extremely long route from the outside of the black hole to the outside of the white hole. In 2018, Hal Haggard and Carlo Rovelli published calculations suggesting we might observe these quantum bounces as tiny deviations in gravitational wave signals from black hole mergers. The difference would be minuscule, parts per million, but potentially detectable with next-generation instruments. Planck stars, the smallest possible objects. This leads to an even more exotic prediction: Planck stars. These would be objects at the very center of black holes, compressed to the Planck density but no further. Not infinite density, just 10 to the 96 kilograms per cubic meter. Still incomprehensibly dense, but finite. A Planck star at the center of a solar mass black hole would be about 10 to the negative 35 meters across, far smaller than a proton, yet it would contain the entire mass of the Sun, supported against further collapse by quantum pressure. This quantum pressure would generate enormous outward force, but the event horizon would trap it inside until the black hole evaporates enough for the pressure to break through. Loop quantum gravity predicts that very old, small black holes might suddenly explode when they reach a critical mass threshold, converting their remaining mass into a burst of radiation. No such explosions have been observed, but if Hawking was right about evaporation, the oldest black holes in the universe, if any small ones formed in the early universe, might be approaching this threshold now, 13.8 billion years later. What if black holes don't have event horizons at all? This isn't as crazy as it sounds. Some physicists argue that quantum effects near the would-be event horizon become so strong that they prevent horizon formation entirely. The idea, championed by researchers like Pawan Kumar Gupta, suggests that as matter collapses, quantum pressure builds up just before the horizon would form, creating a surface of ultra-high-density matter instead of an empty event horizon. These objects would look almost identical to black holes from a distance. They'd have enormous mass compressed into a tiny region. Light would barely escape from their surface, but crucially, they wouldn't have the information-destroying properties of true black holes. These black hole mimickers or dark energy stars or gravastars would preserve information naturally because nothing truly crosses a point of no return. The information remains on the surface, accessible in principle, even if scrambled beyond practical recovery. Observations of Sagittarius A star in 2022 placed constraints on this idea. The Event Horizon Telescope saw a shadow precisely matching the predictions for a true event horizon. If Sag A star were a gravastar or mimicker, the shadow should be slightly smaller or have different brightness patterns. The observations don't rule out mimickers completely, but they make them increasingly unlikely. Nature seems to prefer real horizons. Remember the firewall paradox from earlier? Many physicists thought it was solved by the island formula and complementarity. Not everyone agrees. Joseph Polchinski, one of the original AMPS authors, maintained until his death in 2018 that firewalls might be real. His argument was simple. If information comes out in Hawking radiation, then the radiation particles must be entangled with the interior. But quantum mechanics says a particle can only be maximally entangled with one other system. The paradox: Hawking radiation particles need to be entangled with both their partners near the horizon to preserve local physics and with earlier radiation to preserve information. You can't have both. Something has to give. Polchinski argued that the smooth horizon gives, replaced by a firewall of high-energy particles that would incinerate anything trying to cross. If true, this would mean that old black holes become dangerous. Young black holes might have smooth horizons, but once they've evaporated past page time, their horizons transform into firewalls. The debate continues. Some calculations suggest quantum error correction might allow the necessary entanglement pattern without creating firewalls. Others suggest firewalls form, but only for observers using specific measurement strategies, making them observer-dependent rather than objective features. We don't know. The mathematics is too complex for definitive answers, but the fact that brilliant physicists disagree tells us something important. We're still missing pieces of the puzzle. The most radical solution might be the ER equals EPR conjecture from Maldacena and Susskind. Recent developments have strengthened this idea. In 2023, a team at the Institute for Advanced Study showed that in specific string theory models, you can directly convert between entangled particles and traversable wormholes. The math works like this. Take two maximally entangled particles, add a specific type of quantum interaction, and the entanglement transforms into a geometric connection, a wormhole linking the two particles' locations. If this is universally true, then every pair of entangled particles in the universe is connected by a microscopic wormhole. The universe is threaded with countless quantum wormholes, most of them far too small and short-lived to traverse, but geometrically real nonetheless. For black holes, this means the interior is connected to the exterior by vast numbers of microscopic quantum wormholes. Information doesn't escape through Hawking radiation. It remains connected through quantum wormhole networks. You never really fall into a black hole's interior, you become entangled with it, which is equivalent to being connected through space-time bridges we can't see. This dissolves the paradox entirely, but at a cost. Space-time is far weirder than we imagined. The smooth, continuous space we experience is an illusion. Underneath, reality is a foam of quantum wormholes, constantly forming and dissolving. Some theorists are now exploring whether consciousness itself might involve quantum entanglement, suggesting that the subjective unity of conscious experience could be related to these quantum wormhole connections. That's speculative. What's not speculative is the ER equals EPR connection has survived every mathematical test thrown at it over the past decade. If it's correct, then the information paradox was never really about information being destroyed. It was about us not understanding that quantum entanglement and space-time geometry are the same thing. We've talked about theory and mathematics, but can we actually test any of this? The answer is yes, and it's already beginning. LIGO and Virgo have detected over 90 black hole mergers since 2015. Each signal provides extraordinary detail about the final seconds before collision, the masses, the spins, the orbital dynamics. But here's what most people don't realize. These gravitational waves are quantum mechanical objects. Each wave is a quantum field excitation propagating through spacetime, and quantum fields carry information. Physicists at Caltech and MIT are now analyzing LIGO data for subtle quantum signatures that would distinguish between different theories of quantum gravity. If black holes have fuzzballs instead of smooth horizons, the gravitational waves from mergers should show tiny deviations, echoes bouncing off the quantum structure. If firewalls exist, they should create distinctive features in the waves. If loop quantum gravity bounces are real, they should produce specific frequency patterns. In 2020, researchers claimed to find tentative evidence of post-merger echoes in the data from GW 150914, the first detected black hole merger. The signal appeared to show repeating patterns in the milliseconds after the main merger, exactly as predicted if the event horizon has quantum structure. The evidence was controversial. Other teams analyzed the same data and found no significant echoes. The signal, if real, is at the very edge of detectability. But LIGO is being upgraded. The next generation detector, LIGO A+, coming fully online in 2025, will be twice as sensitive. The proposed Cosmic Explorer, if funded, would be 10 times more sensitive than current LIGO. At those sensitivities, quantum gravity effects should be detectable if they exist. The Event Horizon Telescope gave us the first images of black hole shadows. The next phase is even more ambitious: movies. By 2025, improvements in the array will allow continuous monitoring of Sagittarius A star and M87's black hole. We'll watch matter spiral across the event horizon in real time, frame by frame. If the event horizon is smooth, we should see matter simply disappear when it crosses the boundary, never to be seen again. But if quantum effects are strong, we might see something else. Perhaps matter hesitates at the horizon, hovering just outside for longer than relativity predicts. Perhaps we see quantum fluctuations, sudden brightness changes that shouldn't occur in classical physics. The next generation Event Horizon Telescope, incorporating space-based telescopes, could achieve resolution fine enough to probe scales just a few times larger than the Planck length at nearby black holes. That's the scale where quantum gravity should become visible. Researchers at the Harvard-Smithsonian Astrophysics Center are developing analysis techniques to search for quantum signatures in these future images, asymmetries in the photon ring, time-variable features that appear and disappear, subtle brightness patterns that would indicate quantum information being scrambled at the horizon. Perhaps most exciting is LISA, the Laser Interferometer Space Antenna, scheduled to launch in 2035. LISA consists of 3 spacecraft forming a triangle 2.5 million kilometers on each side, orbiting the Sun. It will detect gravitational waves at frequencies impossible to observe from Earth, frequencies that reveal black holes in ways LIGO cannot. LISA will observe supermassive black hole mergers from across the universe. More importantly, it will observe stellar mass black holes spiraling into supermassive ones, called extreme mass ratio inspirals. These systems are perfect laboratories for testing quantum gravity. A small black hole orbits the supermassive one thousands of times before merging, mapping out the space-time geometry with exquisite precision. If the supermassive black hole's event horizon has quantum structure, fuzz, soft hair, or any deviation from perfect smoothness, the small black hole's orbit will reveal it. The gravitational waves will encode information about the quantum state of the event horizon. Calculations by the LISA consortium suggest they'll be able to test string theory predictions, measure the quantum fuzziness of horizons, and potentially detect Planck scale physics through cumulative effects. We're not talking about detecting individual quantum gravity events; those are far too small. But thousands of orbits accumulate tiny effects into measurable signals. By 2040, we might have direct observational evidence for quantum gravity. Not philosophical arguments or mathematical proofs, but actual data from instruments measuring the universe. You can't build a real black hole in a laboratory, but you can build quantum systems that behave like black holes mathematically. This is what Google's quantum AI team did in 2022. Using their Sycamore quantum processor, they simulated a quantum system with properties analogous to a black hole, a region that scrambles information, a boundary where quantum entanglement behaves like an event horizon, and Hawking-like radiation leaking out. Then they measured how information escapes from this analog black hole. The result: perfect agreement with the page curve and island formula. Information initially becomes more scrambled, then starts coming out in a coherent pattern after the analog of page time. This wasn't a black hole, it was 53 qubits following carefully programmed quantum circuits. But it proved that the mathematical framework underlying the information paradox solution actually works in quantum systems. In 2023, researchers at IBM created larger simulations with 127 qubits, achieving even better agreement with theoretical predictions. More remarkably, they observed quantum extremal surfaces forming dynamically in the simulation, the boundaries between regions that behave like the black hole interior and the exterior radiation. These aren't real event horizons, but they follow the same information theory, and they exist in quantum computers we can probe and measure. Analog black holes in fluids and light. Even more exotic, physicists have created acoustic black holes in flowing water and Bose-Einstein condensates. When fluid flows faster than the speed of sound in that fluid, it creates an acoustic event horizon. Sound waves can't escape upstream. Mathematically, this is analogous to a gravitational event horizon where light can't escape. In 2016, Jeff Steinhauer at Technion Israel Institute of Technology created such a system and detected what he claimed was acoustic Hawking radiation, quantum sound waves emerging from the acoustic horizon. The results were debated, but subsequent experiments by multiple teams have confirmed the basic effect. Acoustic Hawking radiation appears to be real. These systems let us test predictions about black hole evaporation in tabletop experiments. We can measure how information flows from the interior to the exterior through the analog radiation. Recent experiments have even created analog wormholes in metamaterials, specially designed structures that guide light in ways mathematically identical to how gravity guides light near wormholes. These aren't real wormholes connecting distant regions of space, but they prove that the mathematics describing exotic space-time geometries can be physically realized, just in different contexts. What emerges from all these approaches is a new way of studying quantum gravity, not by building particle accelerators that reach the Planck energy, impossible with any conceivable technology, but by creating quantum systems that mimic black hole physics. The universality of information scrambling means that lessons learned from quantum computers, fluid dynamics, and metamaterials apply to real black holes. We're developing a quantum gravity phenomenology, an experimental science of quantum gravity effects built from analog systems, precision observations, and theoretical calculations. The next 15 years will be decisive. LISA launches in 2035. Next-gen Event Horizon Telescope observations begin in the late 2020s. Quantum computers will reach thousands of qubits, allowing more sophisticated black hole simulations. By 2040, we might not just have solved the information paradox theoretically, we might have tested the solution experimentally. Or we might discover something completely unexpected, new paradoxes, new mysteries, evidence that our current theories, despite their mathematical elegance, are still missing something fundamental. That brings us to the ultimate question: what does all this mean for the nature of reality itself?